Good morning, everyone. My name is Sherry Ryan, and I'm the Dean of the Marxe School of Public and International Affairs at Baruch College, City University of New York. First, I'd like to welcome all of you to this Climate Week New York City panel hosted by the Marxe School. Our session today, the role of nuclear energy in decarbonization and powering the AI era, brings together leading voices from around the world, literally. We have people from all over the world sitting in the Zoom room with us. Thank you so much for being here. Leading voices to here with us to discuss nuclear's evolving role in the clean energy transition. At Baruch and across CUNY, we are deeply committed to advancing climate and sustainability scholarship and education through initiatives such as the CUNY Climate Consortium and the CUNY Climate Cluster hiring process and the CUNY Climate Scholars Program. We're working to build interdisciplinary collaborations that bring faculty, students, and partners together to generate innovative solutions that address the climate crisis. Here at Marxe, we're also happy to have launched a graduate specialization in climate change for our Masters of Public Administration students. We're really looking to prepare the next generation of public service leaders who can address climate challenges with the necessary analytic and policy preparation. Nuclear energy, as we'll hear today, sits at the heart of many debates about our future energy system, how we meet net zero goals while ensuring energy security, and now how to respond to the rapid rise of artificial intelligence and its energy demands. So I'm so delighted to welcome all of you for this timely and important discussion. And with that, I will turn it over to our moderator, Associate Professor of Energy and Climate Policy here at the Marxe School, Gang He. Thank you so much.
Thank you so much, Dean Ryan, for your support and for your vision and leadership. I'd like to add my own welcome. Today, we'll explore how nuclear energy can contribute to deep decarbonization while addressing new challenges such as the surging energy demand of artificial intelligence. Today, we are very fortunate to have a group of distinguished speakers who bring global perspectives from research, industry, and policy, not just regional or the global geographically, but also from different perspectives. Now, I have the honor and great pleasure to introduce our keynote speaker, Professor Dan Kammen, who is a Bloomberg Distinguished Professor of Just Energy Transition at Johns Hopkins University. And Dr. Kammen is also elected member of National Academy of Science, has long been the leading voice of clean energy transition, just energy justice, and climate justice. And to me, he is also a lifetime mentor, colleague, and a friend. I really appreciate Professor Dan Kammen can join us. Without further ado, Dan.
Well, thank you so much, and welcome everyone to this webinar. I really want to thank Dean Ryan and Professor Gang He and Shangwei Liu. We'll hear from both of them later on. I particularly want to thank our panelists. Both are old friends. I have to admit, this is a real pleasure. I think when you get old, you get to have old friends and you get to watch them do amazing things. And you're going to hear from Jessica and Nicolas in particular about some of the really exciting innovations that are taking place. I like to say, I think I learned that nuclear was of strong interest to a younger generation by talking to these two. And so we'll come back to that in a second. But I wanted to welcome our audience in on a whole number of different dimensions. We are seeing remarkable changes in policy and posturing and technology around nuclear projects, from some of the work on on liquid metal reactors and uranium thorium systems. Obviously, we'll come to small modular reactors and what they may mean in this mix going on. Significant contracts being signed, both those that are dedicated to topics like powering AI and data centers, and then much more broadly in the energy mix in a whole variety of countries. And so, in terms of both the topic for today, but also the very diverse perspectives on how do we meet zero carbon goals, what exactly does that mean, and what role does nuclear have in that mix. I couldn't be more thrilled than to have our panelists on today, and I'll turn it over to them fairly soon. But I guess the things that I wanted to most highlight and encourage interaction and thoughts by our audience is, to what degree do the technological changes we're seeing and we'll be talking about today in nuclear projects? And I would, highlight that while it's nuclear fission that's on the table, nuclear fusion has made some of the most dramatic jumps recently in terms of new projects. But all of this fits together in a landscape where there's real dramatic pushes to change how we think about the interaction of different energy technologies. So one of the questions that I will come back to is, what are the ways in which innovations, both on the hardware side of nuclear, of energy storage, of renewables, of the use of what I'll kindly call legacy fossil fuels, and hopefully that really means legacy of fossil fuel use with carbon capture, which is not clear, that in thinking about how do we leverage both the technology side, but also the integration side, the smart IT systems, the AI point, not just in terms of a big new demand for energy, but also in an opportunity to really think differently. And I guess I don't think it's a bold statement anymore to say the advances we're seeing on nuclear fusion, certainly what's going on in France with ITER, with K-Star's recent announcements, with the myriad of small nuclear fusion companies, as well as many of the advances in small modular reactors, would not be possible without the advanced computing, the machine learning, the efforts that are going in to really manage these systems in ways that are very, very different than we thought of them in the past. And I hope and expect that all of that will come out. I do have a personal tagline, which I am sure that no one in the panelists or in the audience will agree to readily, and that is that my prediction, coming out of a lot of the analytic work that we've been doing in our lab, and some of the work with emerging nuclear companies, is that I actually think that it's no longer an outrageous statement to say that in 2070, when, barring some miracle, I will not be here to see it or to collect on the bet. I am forecasting a 70% nuclear world, nuclear fusion world in 2070, with half of that fusion being 93 million miles away, meaning on the order of a third solar, a third fusion, and a third the rest. And again, I don't meet many people who agree. Some people will grudgingly say it's on the table, but I'll highlight that to only illustrate the degree to which technologies that have consistently run at a certain percentage of national and global energy, notably nuclear fission, have really dramatic new opportunities to scale up and down what they do based on how smart, thoughtful, and integrative the energy supply and the end use communities can be. And so we will highlight a paper that Gong and Shangwei and I published in late July in Nature. We'll put the link up and in. But it was really a price assessment as well as a technology innovation assessment. And we'll come back to some of these topics as we go. But I am so looking forward to having our panelists give their perspectives from the research, the advocacy, and the integration perspective, both within individual companies, which is critical to making the leaps forward. Some of you have seen some of the dramatic new announcements at Kairos and many other players, but also in terms of how do we take advantage of the strengths of low and zero carbon technologies so that we can build much more rapidly than the policy world appears to be heading to a decarbonized future. And that's really, to me, the challenge. From the 2030 or 2035 goal for decarbonization in Sweden that Jessica will highlight, to the 2045 in California, to the 2060 in China, and a number of other countries. There are hard numbers on the table in terms of promises, but as a physicist who works on climate issue, promises are really only as good as what we think we can deliver. So I'm looking forward to hearing a whole range of perspectives as we go. Let me turn it back to Gong for the introduction of our panelists, but I am delighted to see the audience, and I'm also really, really looking forward to hearing the comments from our speakers. So thank you all so much for being here today.
Thank you so much, Dan, for your insightful remarks. Now let's move to our panelists. I'll introduce all the panelists first, then they can move seamlessly to their presentation or remarks. First, we will hear from Dr. Shangwei Liu. Shangwei is a postdoc researcher at the Harvard Kennedy School who will share insights from his research on China's nuclear development and the deployment experiences and the lessons. Next, we will hear from Dr. Jessica Lovins. She is a senior fellow with Nuclear Innovation Alliances, and Jessica and the co-authors published a classic paper on global nuclear energy costs back in 2016. So we'd love to hear what's the updates and from US perspective on nuclear cost trends, innovation, and the policy pathways. Finally, we'll hear from Dr. Nicolas Zweibaum, and he is the Deputy Chief Technology Officer at HEXANA, who will discuss nuclear perspectives in the EU and including recent developments in advanced nuclear technology and supply chains. So without further ado, let's first welcome Dr. Liu, please.
Let me share my screen. Right. Great. Thanks, Gang, for the invitation. It's actually my first experience in the NYC Climate Week, and it's really my honor to present our recent work published in Nature in this July, focus on I think it's more like economics of the Chinese nuclear power. And I want to echo to what Professor Kammen has been said. This is actually a good timing to talk about nuclear power. It's really hot topic, not only from the traditional players. We see a lot of news from United States, from France, from Japan, and also from emerging countries. Many countries actually are building their first nuclear power plants or consider building their first nuclear power plants. And also we see a lot of interest from private sector driven by AI data center. We have seen a lot of investment, other like promised investment in the nuclear power industry. So this is a good timing. But I want first go back to the history to look at the whole landscape of nuclear power build out. What I'm showing here is the build out of global of the nuclear reactors globally, and we can clearly see that we have been building a lot of nuclear reactors in 1960s, in 1970s, and in 1980s. And after that, it's more like the party's over. When people discussing nuclear power, and usually people will discuss like safety issue or waste disposal issue, like the nuclear waste. But I think one thing is very important here is like many people probably agree with me, like the fundamental problem here, why we didn't see a lot of new nuclear power construction after 1990s is too expensive to build. And I want to explain further on this one before I go to the details, like deal with some terminology. Basically, when we talk about the nuclear power economics, by the end of the day, it's a form of electricity. So we usually use the levelized cost of electricity to measure the cost. It's not a perfect matrix, but it's usually used. And what I'm showing here is a very classic equation to calculate the levelized cost of electricity. Basically, we have the capital recovery factor, construction cost, operational cost, maintenance cost, fuel cost. For nuclear power, we also have the waste disposal cost, and divided all the cost by electricity production. And for nuclear power, what we have been saying is operational cost, maintenance cost, fuel cost has been relatively stable and relatively low. And for most of the time, nuclear power are used for base load. So its electricity construction is also pretty stable. So what really matters in this equation is the construction cost term, which can be divided into two parts. The first is really our focus of our paper, the overnight construction cost. And the second part is the financing cost or the interest during construction. If we have some time, we can discuss that later in Q&A. But I will really focus on the overnight construction cost. The reason why the construction cost is really concerning is historically or empirically, we have observed, I think is a very concerning but also very interesting phenomenon. People call that the cost escalation curves of nuclear power. What I'm showing here is actually the data from the paper by our another panelist, Jessica Lavrin's, a very classic paper about the nuclear power cost in the United States. That's a global paper. I will show a lot of results on that paper, but this is part of from the United States. And what you can see here is actually the construction cost of nuclear power plants has been dramatically increased over time. It has been increased before the 3 Mile Island accident, and after the 3 Mile Island accident, it has been increased dramatically. And there are a lot of factors contribute to this escalation. First, in the United States, every nuclear power plants, every nuclear reactors is built somewhat differently. So there's a lack of standardization. And also over time, the labor productivity has been declining over time. And the material costs, especially like steel, cement, for the nuclear power has been increasing over time. And especially after 3 Mile Island accident, the regulations have been more and more stringent and also keep changing over time. So which makes it difficult to build new nuclear power plants. That's the factors people usually talking about. And as the paper by Jessica Lavrin has demonstrated that this is a global phenomenon. It's not only in the United States, but in France, in Japan, in a lot of countries. What I'm showing here is the cost in France. And you can see it's less dramatic than the United States, but it's still, the cost has been doubled from late 1970s to late 1990s. And people usually say the reason why you see here is like the nuclear power, the nuclear reactors in France has become larger and larger over time and more complicated, which contribute to the cost of increase. When I start seeing this debate, I think people will, the natural question people will ask is that if the cost escalation inevitable, and basically people can argue from two sides. One side, people can say this is because nuclear power is a bad technology, it's risky, it's large scale, it's complicated. Or you can say this is more the problem of the innovation system. It's a policy, it's a system, it's regulation, it's supply chain, it's a business model. I think this debate is very interesting. And as a Chinese, it's very natural for me to think about what's going on in China. Actually, I was really surprised no one has the cost data in China. So I decided to collect some data on that. And I think China is also very special because China is the only country over the past 2 decades has been consistently and substantially expand its nuclear power fleet. So this come to our paper, and I will briefly discuss our results here. Basically, this is our results, and what I'm showing here is the overnight construction cost of the Chinese nuclear power plants, both all the commercial nuclear power plants, both operating and the reactors under construction. We really try to use all the public available data so people can replicate our analysis. We actually get a lot of data from news reports and the environmental assessment reports from a lot of Chinese sources. And we do some very simple adjustment to make that comparable over time. But this is the result we have. I was actually very surprised, and you can see what happened is here, especially in early years, it has been decreased really quick over time. And I think basically the story can be divided into 3 parts. The first is the phase 1, which is really early stage of the Chinese nuclear power industry, which China started to introduce technologies from France, from Canada, from Russia, and also at the same time build Chinese own domestic model. And during that time, you can see the cost decreased really quickly over time. And in 2005, the Chinese government, I think, announced a very ambitious plan to expand the nuclear power capacity. And what happened is like they want to use the Chinese domestic model, the CNP model and the CPR model, and to build a lot of new reactors. And all these nuclear reactors, they actually started the construction before Fukushima and finished their construction after Fukushima. And because of Fukushima, China basically stopped that plan. And what happened is like China want to think about the Fukushima. They want to choose more safer or more innovative technology, which is people usually call that generation 3 technology. And during that time, China already have some experience with the French EPR model and US AP1000 model, and also developing China's HPR model. And after that, especially after I think after 2019, China restarts the whole new nuclear power construction plan and trying to build a lot of new nuclear power plants over the next decades. It's really likely China will surpass the United States to become the country with the largest nuclear power capacity by 2030, if all these nuclear power plants and the construction will be built. So finally, what drives the cost reduction in China? And what we find here is actually basically what's the major driver here is the indigenization process, which means you replace the foreigner labor with Chinese labor, replace the foreigner equipment with Chinese equipment, which usually lower the cost. That's the key driver. But you also can say what really happens here is also quite similar to what happened in French, which when you switch to the more complicated model, usually the costs also increase. And the final figure here is, I think it's very interesting and straightforward analysis here is we compare the domestic content rate of a nuclear reactor with its construction cost. You can see clearly if you have higher domestic content rate, you have much lower construction costs, which is one evidence showing that maybe industrialization was a key driver here, and also supported by many reports, news, and a lot of data for individual reactors. So finally, our takeaways here is like, if you look at overnight construction costs, you actually can feel, I think I'm still really surprised, like different countries have very different cost trajectory. And we actually still have very little understanding on what's going on there. And we are trying to understand more on what mechanism works. But basically, we see, like in the United States, the cost dramatically increased. In France, it's moderately increased, which is still huge because that's double cost. And in South Korea and China, we see some cost decline. And for China, I think our conclusion is like the major the measure to break this cost escalation curves is the indigenization process. But with that, I'm happy to get back to the moderator, Gang. Thanks everyone for coming.
Thank you so much, Shangwei, for sharing this cool paper. Especially, I know there are a lot of efforts involved in the data collection and also how to really interpret the data that find the policy implications for other countries. I think now is perfect timing to move to Jessica. Would love to hear your perspectives on US and how some of or none of this can apply to US.
Yeah, thank you. And it's a perfect tee up. I just wanted to say thank you, Shangwei, and the other co-authors of the paper. I was so excited to see that paper. And I'm actually going to start off with a little bit, just one bit of redundancy, the same chart from your paper, just to kick off the narrative of what I'm going to talk about. So I was very just interested in the data that you were able to get from China and to compare it with the data from my paper on these 7 other countries, particularly the US and France, which are always held up as these case studies of what went wrong in terms of nuclear costs. And so I wanted to take those as kind of starting points to talk about the interactions with policy and nuclear costs and what we can do differently as we're sort of restarting nuclear, especially in the US, but also in Europe. And so looking at these 2 trends, I've sort of simplified the cost trends here. This is the cost averaged by year in all these countries. And so for the US, it looks a lot simpler. And this is also plotted by the year of construction start. So the light blue is the US, the dark blue is France, and the yellow is China. And you can see, the US just escalates a ton. France on this scale looks pretty level, but it does double in costs. And you can see, up in the top right, those really high costs are the recent Vogel 3 and 4. And you'll notice what's really not interesting, but really obvious is this huge gap, this 30-year gap where the US wasn't building. And I think that's really important in terms of what caused this huge cost escalation, this huge sort of restart in the industry. And you see the same thing in France with the Flamanville 3, which is the plant that was finished in, 2007. Or started in 2007. That was also quite expensive. And so besides the lessons that we can learn that Shangwei mentioned on, standardization, indigenization of the supply chain, bringing the workforce, bringing the manufacturing into your country, I think there's also a really important lesson around industrial policy in terms of demand side policies and market pull policies, and sort of creating that demand for not just nuclear, but for clean energy in your country, and creating that consistent pull for clean energy. And that's really what the US has been lacking. Whereas when you look at these other countries, and let me jump to the next graph just to show a country that looks much more similar to China, this is South Korea. Quite a similar trend. The build out is much more paced. So a long gradual decline in costs, but the pacing of their build out is much more gradual. And it's, they have these planned phases of construction. They build a lot more reactors at their sites, more like 4 to 8 reactors at their sites. And it's part of a policy for energy independence that is part of a larger program of industrial policy. And I think that's another lesson that is probably going to be a lot harder for the US and European countries to learn. But there are parts of it that we can learn in terms of demand side or market pull policies. And so that's where I'm going to take a step back because I'm going to stop. Nope, stop sharing. Oh. Because I think in the US, if you've been following nuclear, you've seen that there's been a lot happening, and there's been all these amazing technologies, particularly in the last 10 years. You've probably seen a lot of announcements, all these new companies. There's like 70 plus companies in the US with all these advanced nuclear technologies and small modular reactors. And it feels like very exciting. There's a lot of private investment, a lot of venture investment. But it's hard to know if that's really real and not much has been getting built. And so I wanted to talk about what sorts of policies have been driving that innovation and sort of what sorts of policies are needed to actually get things built. And so there was a lot of investment, particularly from Department of Energy in sort of the 1990s and 2000s, that drove these innovations and these companies, spin-offs from national labs. But there wasn't those demand pull policies to actually get these projects built. And in particular, in the mid-2000s, natural gas was very cheap. So utilities didn't have an incentive to build new nuclear projects. And then you had Fukushima really killed a lot of demand for interest in nuclear. But when we had the Biden-Harris administration come in 8 years ago, they had a very ambitious climate agenda. And they set a target to fully decarbonize the power sector by 2035 and to reach net zero emissions economy-wide by 2050. That's very ambitious. And they were also very supportive of nuclear energy, which was new for a country that had a very ambitious climate goal. It's new to pair those two together. And particularly, they talked a lot about advanced nuclear and small modular reactors as part of their portfolio of climate solutions. And in August 2022, President Biden signed the Inflation Reduction Act into law. And it included a lot of great investments for clean energy, for green infrastructure, but specifically for nuclear, it had a production tax credit that helped keep existing nuclear plants running, and a technology neutral clean energy production tax credit, or PTC, and a investment tax credit, which advanced nuclear could apply for. And there were all these sort of bonuses or top-ups that could raise that tax credit up to $30 per megawatt hour, or 50% for the ITC. If you did things like prevailing wages or you located an energy community, a 50% investment tax credit, that's big. That means you could get 50% of your investment back as a tax credit. And there's also a hydrogen production tax credit. If you produced hydrogen using nuclear, and actually existing nuclear could also qualify for that. And the IRA increased the loan program office's authority and lending authority to loan for advanced nuclear projects. So this was really huge. It was a game changer for nuclear in the US because these projects had never had that sort of incentive, those sort of supportive policies for nuclear. And what it did is it got nuclear projects off the drawing board. It, got concrete projects moving forward. And we started to see a lot of nuclear companies, these, 70 plus companies in the US, start to fill out their order books beyond just first of a kind demonstration. And that's where you started to see all of these big announcements coming out. 2 years later, we also had the Advance Act passed in the summer of 2024, which had a lot of gradual improvements in licensing to make it easier and cheaper. But I think, as Shangwei mentioned, just in the last year, we had all of these big tech announcements and data center announcements, like Google's partnering with Kairos and Amazon's investing in Pennsylvania, and Amazon's partnering with X Energy, and all of these data centers. So some of those happened, in the fall of 2024, and some of those announcements happened in the spring of 2025. So some of those announcements happened after President Trump came into office and canceled US commitments on climate. So you still see those data center nuclear projects moving forward. And why is that if they, don't need to be low carbon? So why is there still that clean energy demand pull policy, or that pull for clean energy if the US doesn't have that climate commitment necessarily at the federal level? So a big one is that data centers and AI, they just need a lot of power, and they're having trouble getting it in the US. So wait times for new gas turbines are really long. The queue for grid connections are long. For some of these companies, nuclear is just a hedge. They're diversifying because they need all the power they can get. But also for a lot of these companies, they have their own climate commitments, and they're still in place. No matter what the US government is doing, they operate in a lot of countries around the world. And so they need a large amount of zero carbon power, and they need a lot of reliable power going forward. So it's an energy independence question, a reliability question for them. So they're still interested in nuclear, independent of what the federal government is doing. So those projects are still going forward. But speaking of policy, so when President Trump was elected, there was some optimism from the nuclear industry, because Trump had said many positive things about nuclear during the campaign, and that did play out somewhat to their credit. So in May, President Trump signed 4 executive orders on nuclear power that laid out very ambitious targets, some which were mentioned by Shangwei. So adding 300 gigawatts of new nuclear capacity by 2050. That's very, very ambitious. That also means keeping an existing 100 gigawatts running through 2050. Starting construction on 10 large reactors by 2030, and then bringing 3 test reactors online by July 4th next year. And then lots of other directives in those executive orders on exports, fuel supply, workforce, etc. However, so these were people got very excited about these. There were a lot of announcements from nuclear companies, a lot of optimism from the nuclear industry. So it felt like, that's the coherent nuclear policy that was missing, that demand pull policy that was missing. But I'm a little more skeptical. I'm going to say why. So the executive orders ask the Department of Energy and they ask the Nuclear Regulatory Commission to do a lot of work, but they don't provide any additional resources. And specifically, the Department of Energy and the Loan Program Office have seen huge staffing losses from the Department of Government Efficiency this year. So who is going to be implementing these programs? Who's going to be reviewing these applications? Who's going to be reviewing these loan applications, these licenses? And one of the executive orders, which focused on the NRC, actually asked that NRC reduce its staffing even further when they're going to be expected to review 300 gigawatts of new reactor applications. On top of that, Congress's priorities don't really seem aligned with this. So the funding bill that was signed into law on July 3rd reduced the funding appropriated for the Loan Programs Office substantially, which is going to result in fewer nuclear projects moving forward. And the restrictions that were put on the foreign entities of concern leave a lot of open to interpretation by the Treasury Department. So that's kind of spooked investors for some projects. They don't know, is this component going to be allowed? Is this, supplier going to be allowed? It's a lot of risk for a project, for an industry that's very risk averse. So the US has really great technologies and a really good investment ecosystem, but they still don't have that committed, coherent industrial policy that we see in China or South Korea, or even maybe in like the Biden administration. So it's getting there, but I think we still have a lot to learn in terms of stable policy ecosystem long term.
Thank you so much, Dr. Loving, for sharing this from historical and future perspective. I really appreciate the insights. Now let's move to Nicolas. And we'd love to hear what's going on in the industry world, please.
Absolutely. Let me, can you just confirm that you can see my screen?
Yeah,
I haven't used Zoom in a long time. Okay, thank you very much. So when Gang reached out, we've known each other for a very long time. I actually used to work, studied and then worked in the US for a very long time. Prior to joining HEXANA, which is a French-based nuclear startup, I was actually the first employee at Kairos Power, which has been mentioned a few times today. And so if there's any questions around Kairos and the Google deal, even though I'm no longer part of that organization, I would be happy to provide some perspective there as well. But here today, I'm more concerned with the situation in Europe, which was this idea behind more of a global perspective around the role of nuclear energy. And so what I'm going to try and provide today is an overview of some of the recent European policies and industrial efforts around a new boost for nuclear, if you will, in France and other countries in Europe. And then I'll talk just a little bit about the solution that HEXANA is developing in response to some of the current needs for power and high temperature heat for industry. The word renaissance has been used so much in nuclear, but really that's what we're seeing now in the EU in terms of policy. The reason I'm saying that first is that there have been a number of recent nuclear policy reversals. Several countries like Belgium, Italy, Denmark either have or are considering lifting bans or phase-out laws that had been in effect for decades sometimes. And for instance, Belgium, which had a phase-out law back in 1999, that was just repealed, and now they're planning on not only extending the lifetime of their current plants, but also building new plants. So that's definitely a change in trend in terms of individual country policies. On top of that, there's a number of key alliances that are both political and industrial. I'm not going to read everything that's here, but just so you can see, there's kind of a recent and steady trend, 2023, with the political nuclear alliance with member states, and then an industrial alliance that I'll be talking about, which is there to support the development of small modular reactors and advanced modular reactors in the EU since last year. And then more recently, a number of industrial federations across Europe
Nicolas,
that have,
yeah. Are you advancing your slides? We cannot see it.
Oh, are you seeing the slide that says alliances expanding or not at all?
The title slide. We can only see a title. So probably need a
okay,
to full screen.
Let me see if I can stop this and start again real quick. If that doesn't work, then I may have to change. Let me see this. Okay, I'll just share the entire screen and try again. Okay,
yeah.
Can you see this now?
Yeah, now it works. Great.
Okay, very good. Yeah. So I was talking about first the policy reversals and then a number of alliances expanding. And so a number of highlights of recent industrial policies. In 2024, there was a Net Zero Industry Act where nuclear was listed in addition to other clean energy sources as strategic to support the decarbonization of industries. And that opened up a number of opportunities for supply chain support and financing. In addition to that, there's a number of financing initiatives, and one thing that has emerged recently is this idea of important projects of common European interest. So that's an opportunity for several European countries to team up and propose nuclear projects that would be supported by with funding from the European Commission for industry partnering with nuclear projects. So that's really important for the prospect of financing for those new projects. And then in addition to that, there is a program by the EU to assess nuclear investment needed by 2050. And the current projection is that we would get to 110 gigawatt capacity with large reactors. A lot of them would be extensions of existing power plants that would keep operating, in addition to 35 gigawatts coming from small modular reactors and advanced modular reactors. So you can see there's a very bullish attitude now by the European Union, the European Commission in particular, to support and expand the use and applications of nuclear technology. Specifically, the European Industrial Alliance on SMRs is a very important recent initiative that was launched by the Commission. It brings together several hundreds of organizations across utilities, tech providers, research institutes, and others. And the mission there is to accelerate the development, deployment, and commercialization of small modular and advanced modular reactors. This is an initiative to develop nuclear in Europe, not necessarily with European technology. So part of that alliance actually includes a number of US designs, UK design, and the UK is no longer part of the EU. So the idea is more about the application and development of nuclear as long as technologies exist, more so than supporting European technologies per se, which is an interesting take on that. And that organization actually just launched a strategic action plan for the next 4 years. That was just this month. That reemphasizes a number of priorities, including identifying technologies, 9 projects that got selected in 2024, and there's going to be a second round of selection supposedly later this year. Strengthening the supply chain, fuel, raw materials, industrial capacities. That's a big part of the explanation why there's been so much change in cost of nuclear over the years or decades. And so definitely Europe is trying to tackle that issue. Also facilitating investment and financing, because there's huge barriers for new players in terms of financing their first plants. And also more regulatory coordination. The reality is that developing a plant, say in France, if you're only going to deploy it in France, is not going to be very helpful, and probably you're not going to be able to get those economies of scale that everyone is touting, especially with small modular reactors. And so the idea is more exchanges between regulators from different EU countries, so that when a design is developed and built in one country, that it can quickly be expanded to the rest of the European Union. Public engagement is another big piece of that. And finally, engaging with industrial end users. And so to that end, there's been a number of technical working groups that have been developed to support projects. And an important one is the first working group on industrial applications. This group is in charge of evaluating energy needs, not only for electricity, but also heat and other carriers like sustainable fuels. All of them would be potential end users for SMRs. Also identifying challenges faced by end users and providing both technology and policy recommendations. And then very importantly, for a company like ours, evaluating and prioritizing demonstration or pilot projects, and being able to say, well, with this application in that country, with this level of power needed and that temperature, that this or that technology would be more or less suitable. There is actually, because the part of the topic was around the AI era, there is a data center subgroup specifically within that industrial applications group that HEXANA is co-leading. And there's going to be an upcoming report on the potential of SMR data center integration in Europe to provide recommendations to the European Commission. So very, very timely discussion today, and I'm very happy and proud to be part of an organization that is part of those efforts for Europe. Now, on that use for powering data centers, a number of key facts here in terms of energy requirements to support data center expansion. What we need first is continuous operation. You need 24/7 operation without downtime. That requires stable, flexible, uninterrupted power. There's also high power demand, and that's rising obviously very quickly. So that obviously requires high power capacity, and that's why our panelists said, you know, there's many energy solutions today, but we kind of need them all if you want to reach the power demand that we're forecasting, including in Europe. The next thing is redundancy and backup. That's key to meet service level agreements. Uptime guarantee is absolutely critical. And so we need backup solutions to ensure power availability during disruption. And finally, there's a growing need for flexibility, just because there's more and more uses that vary over time that need to be coped with. And that's where technologies like what HEXANA is proposing, but we're not the only ones, is particularly interesting, because you're coupling modular reactors with flexible power production. In our case, we're coupling to thermal energy storage to be able to store energy for long periods of time and meet demand flexibility. And then you're integrating that directly with either industrial clusters for heat production or power production when it comes to data centers. That kind of meets all the needs that you can see on the left. So you get continuous reliable power with the reactors operating in base load mode. You have relatively high power production. So in our case, a HEXANA platform can supply up to 335 megawatt electric. You get redundant power generation on site. In our case, we have 2 modules on one side with asynchronous maintenance and fuel reloading, so that you have at least 50% of capacity always on. And then finally, in our case, coupling to thermal storage, you can ensure a highly flexible power supply without compromising the economics of your reactors, because the reactors are operating all the time, and what you're modulating is the output from the thermal storage units. So that's just an example of how new technology solutions can meet the new needs. And beyond electricity, I just wanted to end on this note. Advanced nuclear for industrial heat is another very important aspect, at least in Europe, that we're seeing emerge. More than 25% of CO2 emissions in Europe come from industry, shipping, and aviation only. And so what a company like ours is trying to achieve is not only meet new electricity needs, but also high temperature heat needs from all the industries represented here. And you can see very large amounts of CO2 abatement achievable if we can develop our technology, as well as the associated power needs. So that's what I had in a nutshell, especially focusing on European policy and some of the technology solutions. And I'd be happy to answer questions on either of those. Or if you have questions about Kairos and Google, as I said, I can also try and tackle them.
Thank you so much, Nicolas, for sharing EU policy developments and the technology innovation as happened example in your company. So those are quite exciting. Thank you again for to hear from our speakers, and I'd like to come back to Dan. I know you mentioned a lot in the chat, and also your comments on the importance of individualization to build the local supply chain. So maybe you can share some your comments there, and we can have a discussion.
Well, happy to comment briefly. And as expected, I learned a lot again from Jessica and Nicolas as well. So thanks. And we'll come back to the comments, particularly in your last slide, Nicolas, I thought on some of the heat applications get really interesting, because I do feel that the nuclear community has not taken advantage enough of the diversified load opportunities. And so there's a really nice slide to see that put together. So, but on the point that Gang mentioned, I really think it came out of the detailed work that Gang and Shangwei led in terms of looking at how did different components of the nuclear supply chain become indigenized in China is a really interesting feature. I actually think, I don't want to oversell it, but I think it's one of the stages where we're sort of getting to a more fundamental feature than the really interesting curve fitting that typically goes on in terms of looking at to what extent is the learning curve in solar or batteries or nuclear valid. I think it's a great place to start, but it really opens the conversation, doesn't close it. And so I'm very interested in this feature about the learning that China has done. I'm actually thinking that a next key paper is likely to be what is the learning within and between SMR companies, and then a paper after that, what is the learning going on in the very large number but very high claim but low probability effort in all of the small fusion companies that are coming. And I think it's a really key feature. So to focus on your question here, to me, the curve that's in the paper that we posted in Nature showing the cost declines, but really highlighting the cost within China as a function of which components are being either fully made in China or adapted versions of things that were done elsewhere to meet the Chinese, the Chinese technical specs, is a really interesting feature. I think this opens up a new window to think about learning curves more broadly. So I'm excited to see it. But I guess I'll throw the concern out, and that is that I would say for the results in our paper, we answered the question that we could answer. And it's really interesting, but it's not that surprising. And I'll really be keen to see what Jessica and Nicolas think about the fact that we have old reactors in France and the US. But by comparison, we really don't have old reactors in China and Korea. And so, to my mind, we did a fine job answering the question that the data allows us to answer. But what I really want to ask is is these escalation of costs that we've seen very strongly in the US and it's there in France, but maybe not quite as strong. Is that really an inherent property of these large scale fission machines, or is that due to, this bad dialogue between regulators and investors in the US? And so I'm excited about what we're seeing next, but I really think that, the long-term issue of cost is one that we're going to have to think about in this bit broader way. So I'll be keen to hear what Jessica and Nicolas say about, or their impressions on what's going on here as well.
Thank you, Dan. Jessica, I see your hands or not. Yeah, please.
Yeah, really quick to the point I wasn't going to make, but which Dan just teed up. There was this really interesting result from the French data, which is that plants that were more expensive to build actually had better performance, as in they have less maintenance costs and less downtime, less unexpected downtime. And so you get more electricity out of them. And so that's something, that's important, and they might be, more profitable in the long term. And now that we're seeing this emergent trend of long-term operations. So in the US, we're not just licensing reactors past 40 years, we're going past 60 years, we're going to 80 years. This is a trend in Europe as well. And soon we might be going to 100 years. And as long as it's economic and safe, and you can prove that, I mean, these are very serious and long-term investments. And so thinking about, is the investment worth it? Is that capital investment worth it? If it's not just a 20-year investment, but a 100-year investment, you start to think about those capital costs a little differently. But that's tough. That's tough for a venture capitalist to think about, of course. But I wanted to answer Manuel's question about what are the leading theories for the differences in cross-country cost differences, because that was the whole point of my 2016 paper. And I think Shangwei and Gong and Dan got at this in their China paper, but standardization is a big thing. So you see this with the French data. They saw, starting to see some maybe cost constraints on cost escalation when they were building standard reactors, but when they switched to a new design, cost jumped. And when China focused on building a domestic design or switching towards a Chinese design, or Korea focused on a domestic Korean design, that's when costs really start to come down. And when they focus on increasing the domestic content, that's when costs really start to come down. But the standardization, I think, is key, because you can really increase the learning of your architect engineering firm, of your suppliers. So standardization, yes, but also vertical integration, which is a lesson that is not very transferable. That's very tough for the US, especially to learn. It's maybe a little easier in European countries. And what I mean by that is that, in France, especially historically, you had one utility and you had one company building the reactors. So they could share experience and they could share learning across the construction projects. In China, you have fewer utilities, you have fewer companies building the reactors. You have a lot more geographic spread, but you can still share easier across firms. But in the US, we have 1,300 utilities, not that many building nuclear, but historically there were many different companies with nuclear designs, many different architect engineering firms, many different reactor designs. Nothing was standardized across all these things. So just disaster in terms of vertical integration. And so we're sort of the worst of the worst. So that's a tough lesson for us to learn, but I think the hope is with small modular reactors and factory fabrication, you can move some of that learning into a factory setting. And that's where you'll get some of that learning in one place. And so that's where you can take some of those lessons learned and integrate, have some of that vertical integration there.
Thank you, Jessica, for highlighting the importance of standardization. Nicolas, Shangwei, you have anything you'd like to add?
Well, I fully agree with everything I just heard, and that's the unfortunate thing we're seeing today. And if I take the French example, the EPR was the first plant that was built after a very long time of not building plants. And I think the number is actually off the chart that you were showing, where it actually settled because it went into operation very late compared to what it was supposed to be, and cost kept escalating. And the unfortunate reality is that France is talking about building 6 new reactors, and instead of building EPRs, they're talking about EPR2, which is an evolution from EPR. And so who knows where the learning curve is going to get us in terms of going for a new design again, as opposed to trying to build one more of those. The reality with SMRs, it's not just the factory setting aspect of things. It's also the opportunity to get a new supply chain mobilized early in building smaller chunks of your plant as you go, if you will. And we're seeing this from the design phase. So it's not only when you get to building the actual thing that you realize that, but there's aspects of the design phase where you have to build small parts of your plant, if you will, to qualify new materials. And that's where you lean on a new supply chain and you get them trained. And instead of being trained on building the massive 1 billion euro thing from the get-go, they get trained along the way through iterative design, build, qualification plans that we have at component level, subsystem level. And that's another very important aspect of the M in SMR is modular. And we often talk about factory build and all of that exciting stuff, but it's really about being able to embark your supply chain earlier in the process and building smaller parts of the plant as you go. And we haven't fully realized that potential yet because there's no SMR being built in Europe at the moment, but we certainly hope that this is going to be another positive aspect of the way we're approaching design and build out.
Thank you, Nicolas, for sharing how this might work in the SMR design. I appreciate that. Shangwei, do you like to add?
I just want.
Yeah, go ahead.
Yes, I just want to echo the question, like what's the key mechanisms between the different countries have different costs. I think like people always asking like why Chinese solar is cheaper than US solar, like Chinese nuclear is cheaper than US nuclear power. And I think most of people actually discuss either on labor cost or subsidies. I still feel like the key here is actually the scale of the industry and the scale efficiency, and also that scale gave the whole supply chain that efficiency. I'm trying to do some study to more use academic approach to prove that, but I feel labor costs and subsidies actually only contribute very marginally. That's my opinion, but hopefully I can do some study to prove that.
This is very interesting as we discuss the driver of the learning curve and the differences between different technologies, especially difference between nuclear and other clean energy technologies. This is what we have been discussing. With more component level data and more detailed data across technologies, we may have new insights on those ends. Great, thank you so much on this. Next question, our attendees, please feel free to submit your questions on the chat or on the Q&A. We will have time to discuss your questions, but before we move to that, I have another question that I'd like to ask our speakers. So we have been focusing on the costs, but there are other moving pieces so if we want to make the nuclear resurgence as a reality as they plan, right? What are the policies that you think are important to enable such, scale up or build out? Let's see who. Shangwei, you want? Okay, great.
I can start because I saw audience ask something on the safety issue. I think it's very important, but I want to make a comparison between either nuclear power or SMR with airplane. Like if you think about like the air crash, it's still a risk, right? And you see a lot of air crash that commercial flight industry is still over there. I think a key reason why nuclear power is different from commercial flight is if you have a nuclear accident, the damage is to the public and also the damage is global. And if you have air crash, usually the damage is localized and privatized. And I think for nuclear industry, if they want to address like others other than the economics, like if you want to address safety issue, we need to think about some way, either from engineering approach or from business models, try to privatize and localize the nuclear accidents. And I usually say, if you want to persuade people nuclear power is safe, the only thing we can do is to have more nuclear accidents. And if we have more nuclear accidents and we prove that damage can be localized and privatized, people will feel safe, like they feel like about the commercial air flight. And I didn't see any way that in near term we can approach that, but I think that's very important.
Thank you. Dan, you are
Maybe I
muted.
can.
So Shangwei,
okay.
can I ask you to extend that in a tricky way? And that is, and it gets back to something that Nicolas said about SMRs, and that is inherent in the claim about SMRs providing this kind of new pathway. It's not just the supply chain, it's that the take back of reactor cores and the management of the spent fuel in a centralized, organized way is going to contribute to that process, both on the cost side and the safety side. And I guess I'd love to hear each panelist comment because I'm not supposed to say this on open air, but I remain somewhat skeptical that that aspect is going to buy us much if SMRs really take off. But I'd love to hear what you all think.
Well, I'd like to provide a little bit of a technology perspective on all of this. First of which is that everything we're talking about today, when we talk about advanced reactors, right? Everyone talks about advanced reactors, and the public doesn't always know what that means, except that it's new and it's different from what was before, right? There is actually a number of key common traits around those reactors, which is around enhanced safety. And I can speak to the US experience because I worked there for a very long time. I can speak to the French experience because I work here now. And in both cases, there is this expectation by the regulator, which is already very stringent around regulation of existing operating plants, that new plants are going to have features that make them safer than the previous generation. And so I kind of like it's kind of a twist in the way that Shangwei was presenting things. I wish there weren't so many nuclear accidents so that we can learn what the consequences are. But the fact that an incident is never going to have serious consequences, we should publicize that. In other words, that something failed at plant A, B, C yesterday, but there were so many, including passive safety features, that didn't require any intervention by public or operators, that things got to a safe state and nothing bad happened, if you will. This is a very important aspect in terms of technology and public acceptance that we can't work around. Around fuel, that's a tricky issue because the way to deal with that is so different, especially between the US and France. So obviously, the design that HEXANA is developing at its core is the idea of closing the fuel cycle, as we call it, which is that ultimately you're able to reuse the contents of spent nuclear fuel and use it in the type of technology that we're developing. So that's the most virtuous way of using this technology, if you will. It's very different from what people are touting in the US right now, where there's less of a constraint around resources and a bit less of a constraint around places to store the waste until we know what to do with it. So I won't speak to that, but there's certainly many technology solutions to everything that you just described. And unfortunately, it all comes back to economics when people have to pick between one or the other. And the reason why closing the fuel cycle is more attractive to a country like France is because we don't have domestic uranium reserves, and enrichment is a costly process. And so all in all, there's very big economic factors into doing that. But yeah, I'll just say there's always been technology solutions. The reason why they don't always pan out is because the economics hurt in the end, and it all depends on context, and it all depends on offtake. And with new industrial uses and electricity demand, that equation may change. That's what we're thinking at the moment.
Thank you so much, Nicolas, for the technological perspective. That also answers a question from our attendees. Jessica, you'd like to? Okay. So that's great. Our next question I hope to ask our speakers is on the industry policies. We know, different countries have different background, and at the same time, the nuclear technology has its own merit and pros and cons. So from your perspective, what if you have to choose from all the different industry policies, what do you think potentially most effective in the countries you are interested, or from US or from EU, from China? What do you feel most needed? Okay. Jessica?
Yeah, I
Okay,
can
great.
start. I have more of a historical perspective of what we can learn from history. So I think for a lot of new energy technologies, where we see most successful early adoption or early deployment is from kind of niche users. And so I think we're already seeing this with nuclear, but I think probably the most successful kind of first deployment for nuclear is going to be from industrial users. So probably a data center building nuclear on site just for them, because they have the money, they have the demand, they can site it on their property. It gets around a lot of issues. So I think that's probably going to be the fastest path, the kind of the first demonstration of some of the advanced nuclear. But I think it'll be different in different countries. So
thank you.
And we've already seen a lot of these announcements.
That's probably what's happening in the US, right? The industry shows the interest to nuclear. Great, thank you. Shangwei.
I want to say something on the demand side. I feel in many cases, if you look at the historical data, when nuclear power has been growing really fast, usually you have huge demand for electricity, either in China or in the United States or in France. The problem is like many people discuss like AI or data center today, and there's still uncertainty like how much electricity will be increased from data centers. Suppose like would be 20% in next decade from data centers. Like maybe a fraction of that can be met by nuclear power. And I think the scale is really matters. If that scale is huge, sometimes you can have industrial policy really to make that happen. If that scale is so small and maybe renewables get cheaper or other technologies can really meet that demand, if the society doesn't have the need for the nuclear power, I would feel any type of industry won't work in any way.
Thank you, Shangwei. This also there's a demand drive of the building up. Thank you, Nicolas.
Yeah, I mean, maybe to build on that goes back to the last slide I was showing, right? Surging electricity demand for AI data centers is one thing, and that's obviously what's pushing current plans. I know that well in the US for new build outs of nuclear. That was kind of an unexpected off-taker for all of that electricity that we weren't even able to produce. But needless to say, there's other energy needs beyond electricity, and the potential. So another common trait technology-wise across all the so-called advanced reactors is they all operate with higher temperature fluids compared to pressurized water. And that opens up a huge new market for high temperature heat that was not available from the current fleet of light water reactors. There are applications for the heat from light water reactors, and there's actually companies even in France that are just focusing on that, district heating even. But from an industrial perspective, that's obviously a huge new potential. And that has to come from clean energy initiatives, because if we can keep using fossil fuels to power, steel making or fuel transportation, then there's no point, right? But if there's ambitious climate goals, and currently the EU is continuing on the trend to try and achieve ambitious climate goals in a relatively near future, then that's where those technologies can play a huge potential. So you need this kind of steady climate policy, and I guess that's the theme with Climate Week, right? To make sure that there will be this realized potential for these technologies, because between now and when we're actually able to deploy a high temperature reactor that can deliver that carbon-free heat, if policy changes and you can keep burning gas or something else, then that won't really matter anymore. So I think that visibility and continued support for low carbon or zero carbon energies, including nuclear, is critical.
Thank you, Nicolas. Jessica.
Yeah, I know it's Climate Week, but I did want to bring up this point that, the reason we built so much, or the big push for nuclear in the 1970s had nothing to do with climate, but was the oil crisis in the 1970s. And the big push, or the big change that caused so many European countries to rethink nuclear in the last few years was unfortunately not climate, but was the gas crisis after the Russian invasion of Ukraine. And so I think, I'd love for people and governments to be more focused on climate, but energy security and energy independence, I think, is still a really strong driver of interest in nuclear. And I think that's going to extend beyond the power sector. And that, as Nicolas just mentioned, with heat and industrial heat, I think that might be a growing market for nuclear as well. And yeah, just learning from history again.
Yeah. Thank you so much. These are both, from history and can offer lessons or insights on our projections about the future. I'm trying to get the questions from our attendees. Some of the questions they raised are already discussed. Let me see. There are questions along the financials. We are focused on the costs, but there are other, financial mechanisms that are potentially important to make the nuclear resurgence happen. So can you comment on the other costs, not in addition to the construction costs that we have been discussing? I mean, we touched the safety, we touched, fuel and other, about their potential other costs that we haven't discussed.
I can speak to this real quick, because design to cost is at the heart of our current design phase. And when you look at the various factors that go into the LCOE estimates that Shangwei was talking about, you actually realize that the cost of capital, just the cost of money, is the number one variable in the outcome of that calculation. So obviously, the first level is you count the numbers of tons of steel and concrete that go into your design. It does play a role, but people tend to think, oh, that's the way to optimize. No, the way to optimize is to get cheap money from a big bank, or when it comes to the European Commission, have loan guarantees or a number of other mechanisms to get your financing at a lower rate. That is happening in a number of cases. There's recent examples of EDF, the French utility, getting preferred rates around financing for projected plants in the UK, in particular, that they're building or planning on building. But there's no standard policy around that, and it's still a battle. At least I'll talk at the European level, to ensure that nuclear can constantly get the same rates of financing that other clean technologies are getting. And I agree with Jessica. It's nice and neat to think that the climate policy alone is the driver, but in this case, the number of countries in Europe that are getting onto the nuclear choo-choo train is obviously because of the geopolitical situation as well. But if that trend continues, for better or worse, that should go with easier financing for those projects, and that's really a key factor. So I just wanted to highlight that's a very important question, because we do see that in our current cost estimates, this is the #1 variable, and that makes a difference between $55 per megawatt hour to $120 per megawatt hour sometimes, depending if you have 2% or 10% with average cost of capital.
That's great. Thank you, Nicolas. Any other comments on Dan? I think.
So yeah, I know we have some questions still stacked up, and we only have 8 minutes left. But that question leads me to another point, and that is that what do you think are the best ways for nuclear, if you will, to play nice with other low carbon technologies? There's been some papers out there about the degree to which nuclear could do more load following than it's done in the past. And there are some people who think that, well, SMRs provide a different way to do load following, because you could be directing some reactors to be making hydrogen, although there is an issue about the temperature for hydrogen versus electricity. But you could be essentially subdividing your nuclear facility. And so I wonder, do you think that's a big issue? Because as someone who comes more from the renewable space, I find this to be one of the big tension areas. How do these areas work collaboratively, not essentially in competition for low carbon, both policy space and funding?
I can share one thing is actually I came across a study showing that if you have more demand response or a more flexible grid, actually it will increase the nuclear power expansion. If you do the modeling exercise, you will feel like if the power grid can be more flexible, we need more nuclear power. So I think that's maybe one thing really actually important for nuclear power, I guess. For other part, either demand response or other flexibility problem.
Yeah, I think just really quick, I think more and more modeling is showing that the cheapest, fastest to decarbonize systems have a good mix of renewables and nuclear. And just like the more we can get that out there and the more nuclear people talk about the importance of having renewables, and the more renewables people accept a little bit that you're going to need some base load, whether it's nuclear or geothermal or maybe even fossils with carbon capture, I think that it'd just be great to have more of that kind of we're all in this together language.
And if I take the European perspective, I mean, there's no way around the fact that there's going to be a huge boost in renewable power production over the next decade or even maybe a couple decades, because decisions to build new nuclear reactors today won't lead to nuclear power going online until maybe 2032, 2035. So it's a false argument, I guess, in that it's obvious there's going to be more renewable penetration onto the EU grid. That's the very reason why HEXANA as a company and a technology made the decision to couple energy storage to its reactors by design. And that's because you can run your reactors in baseload mode and produce 100% of their nominal capacity all the time and not modulate at the reactor level, which is an economic burden and also kind of an issue on the physics of the reactors. And
it's a technology challenge for sure.
It's a technology challenge. And so if all of this is borne by the conversion cycle and the thermal storage unit, and you're not touching your reactors and essentially as they're on-off mode, that's a really great combo, or at least that's what we're defending. So It's all part of our projections. We usually, when I have more time and talk about our technology, that's really in the context of increasing penetration of renewables on the EU grid, and this idea that a country like France is not going to replace 60 gigawatts of current nuclear power production with 60 gigawatts of EPRs. That would not make sense, because you'd have to modulate them so much that you would lose a lot in terms of the capex that you invested to begin with.
Great, thank you. I'd like to pick up the question from our own student, Pooja, on the climate extremes impact to the nuclear industry and potential disasters. Do you see climate would have impact on the Jessica?
I was just going to say that I did say earlier that the nuclear industry is very risk averse already. And so nuclear power plants are designed for what we say N+1 events. So they're usually already prepared for hurricanes that are more extreme than you would ever get at the site, or flooding than you'd ever get at the site. They have, of course, things happen that they were not prepared for, and but usually they are over prepared for the types of weather or climate events that they'd get at a site. And so they are, of course, already in relicensing, at least in the US, and I know for a lot of European countries as well, like in France. When they're relicensing, they are taking climate changes or climate change impacts on events and weather events into account in terms of, okay, sea level rise and chances of fire, chances of extreme weather, into changing in terms of risk, the risk of flooding or the risk of hurricane. So they are taking that into account.
Great. Thank you. Let's see. There's another question. I think that can be our last question, given the time. What are the from Fiona? What are the most important supply chain components to reshore? I guess let me rephrase the question. If we like to standardization, like they build a domestic supply chain, what the priority should be given to? Components, or what should be the focus?
Well, there was a lead in the way the question was asked, because I think fuel was mentioned as a potential answer. And the thing with fuel is that it's so strategic that beyond the idea of a supply chain, it's all about political implications and really big players having a say. And so if you're a country that's already nuclearized and has fuel supply capacity, then that's good. If you're not, it's most likely that you're going to buy fuel as a supply from countries that are already equipped with the capacity to make fuel and deliver it. So I don't think that would make a big difference in terms of deployment potential. It will just come from where it's able to come already, if you will, and there's only a handful of countries. I think strategic components are usually those that are closer to your reactor per se, right? And so anything that's within your reactor vessel and all of your safety related equipment, that's usually the more onerous part of your plant. And so in this idea that domesticating contents of plants is one way to get to lower costs, starting there is probably the most critical. And it's not impossible. It's not like this is so unique technology that no one can make it if they haven't before. It's more a question of setting up the supply chain and the quality of the supply chain that comes with it, because obviously the pedigree of those components I'm talking about is the most stringent of all. That would be my perspective on this if I try to kind of decompose the cost as we see it.
Thank you.
I was just,
Jessica, please.
can I just add really quick?
Please.
We depends on the country, but you don't necessarily need to reshore everything. And so I'm in Sweden now, and it's a very small country. They're not going to bring every component manufacturing to Sweden. The US can bring a lot more back, but I don't think necessarily they need to be mining all their uranium in the US borders. So thinking about where do you need to de-risk some of the supply chain and where can you friendshore in terms of making alliances in the supply chain and having sort of security in the supply chain with where you're getting the supply from. And maybe there are areas where you really want to manufacture something in your own borders, but I think de-risking the supply chain can be something you focus on more if you don't have the market to really bring everything back into your borders.
Thank you so much, Jessica. I know this is a very important topic, and if we keep discussing, it may take hours, and we can keep discussing. So we are approaching the end of the session. I do want to give each of our speakers an opportunity to summarize a take-home message you'd like to share in one sentence. Who'd like to go first? Dan, I think, please.
I mean, so my closing sentence would be that we need to catch up on the policy and on the integration that the technology is now opening the doors to for nuclear to have a role.
Thank you. Shangwei.
My message is like this interdisciplinary approach. We need engineering, we need policies, we need a lot of different knowledge here. I hope we can continue the interdisciplinary discussion here.
Thank you, Shangwei. Jessica?
I would say we need more demand pull policies that value the low carbon attributes of nuclear power, whether it's at state level, country level, or even community level.
Thank you, Jessica. Nicolas?
Yeah, in my mind, the key thing that's happening right now is we're seeing that nuclear has new potential. And so I think along the lines of what Jessica was saying, there's a policy aspect, but there's also an industry aspect in that we need to realize what industries can benefit from the positive aspects of nuclear. And this is where the future of nuclear will lie, is if there is an actual need for it and what it can offer, including with emerging technologies that are different from what the prior generations could achieve.
Mm. Thank you, Nicolas. That concludes our session, and I want to thank you again to our experts for such an engaging discussion, and thank you all for joining us today. This conversation highlights both the promise and the complexity of nuclear energy in meeting climate and surging demands. So I would like to thank Dean Sherry Ryan for your support and the Marxe School staff for their wonderful work to put this together. This includes Diana, Amanda, and Zoe for their extremely helpful work. Please continue to follow our work at the Marxe School, and I hope you enjoy the rest of the Climate Week. Thank you, everyone. Have a good one.
Thank you.
Thank you all for joining.